In this video, we're going to look at the Compton scattering effect. A little bit of a background and introduction. Compton scattering, or the Compton effect, is the change in wavelength of a scattered photon after colliding with an electron while it travels through some material. This effect was founded in 1923 by Arthur H. Compton when he observed the scattering of X-rays from electrons in a carbon target. He observed that the scattered X-rays had longer wavelengths than the incident rays. Compton had determined that the scattered photon had a lower energy but a longer wavelength proportional to Planck's relationship. The results of this experiment are important to the field of physics because it further confirmed that light behaves like a particle and it cannot be explained purely as a wave phenomenon. Compton was awarded a Nobel Prize in Physics in 1927 for his discovery. So a little bit more about the concept of Compton scattering. Compton scattering occurs when an incident X-ray photon is deflected from its original path by bouncing off an electron. So as you can see here in this picture, the blue here is our incident X-ray, and it collides with a stationary electron shown here in black. And when the two collide, the X-ray is deflected off of its path of travel by some angle theta, and is now shown here in green. And the electron is also ejected from its orbital and deflected, and is now shown here in red. When the incident X-ray photon collides with the electron, we can use the laws of conservation of momentum and energy for an elastic collision to find the momentum of the photon moving at the speed of light, c, which is given by the equation p, where p is the momentum, is equal to the energy over c, where we can have an equation for the energy given by Planck's constant times the frequency over c, which is equal to Planck's constant over the wavelength. When the incident X-ray photon and the stationary electron collide, the electron gains some energy from the interaction when it is ejected from its orbital. We can find the energy of the electron using the equation E electron is equal to the initial energy of the incident X-ray photon minus the final energy of the X-ray photon that's deflected here. So the energy lost by the photon is equal to the energy gained by the electron. And as we can recall up here, this relationship that we have for energy, so this is equal to hc over lambda initial minus hc over lambda final. Since the scattered photon has less energy than the incident photon, the scattered photon has a longer wavelength, and we can calculate this change in wavelength using the equation delta lambda is equal to lambda final minus lambda initial, which is equal to h over the mass of the electron times the speed of light times 1 minus cos theta, where again theta is the angle through which the scattered photon is deflected. Now that we know a little bit about how Compton scattering works and some of the governing equations, we can do a few examples. First, we're going to find the scattered photon's wavelength, so lambda f here, and I've chosen for our initial wavelength 0.03 nanometers, and for theta, the angle through which the scattered photon is deflected, to be 30 degrees. And here I've just summarized our equations that were shown just a couple minutes ago. So in order to find the final wavelength, we want to use this first equation here. So lambda final is equal to lambda initial plus h over m EC 1 minus cos theta. So we have all of the parameters here that we're interested in for calculating the final wavelength, so we can just go ahead and plug those in. So lambda final is equal to 0.03 times 10 to the minus 9 plus Planck's constant, which is 6.626 times 10 to the minus 34 over the mass of the electron, 9.11 times 10 to the negative 31 times the speed of light, 3 times 10 to the 8, multiplied by 1 minus cos 30 degrees. So plugging this into our calculator, we get lambda final is equal to 0.03 times 10 to the minus 9 plus 2.424 times 10 to the minus 12 multiplied by 1 minus cos 30. And if we plug all this into our calculator, we get a lambda final equal to 3.0325 times 10 to the minus 11 meters. So this is equal to 0.030325 nanometers. So if we compare this value to what we had originally for our original wavelength, it's not too much bigger, but the wavelength does get bigger when the photon is scattered by a collision with the stationary electron. Next, we are going to calculate the energy gained by the electron due to the collision, and I've just recorded our value for the final wavelength of the photon up here, so we have it to refer to. So using this equation, we can calculate what the energy is that the electron gains due to the collision. So we have E equals hc times 1 minus lambda initial minus 1 over lambda final. And I just want to make a note, since I've noticed here that I'm using the 0 or the naught symbol and I interchangeably for the initial wavelength. I just want to make a note of that. So here again we have all these parameters, so we can just go ahead and plug them in. E is equal to 6.626 times 10 to the negative 34 times 3 times 10 to the 8. And then our lambda values, we have 0.03 times 10 to the minus 9 over 1 minus 3.0325. I'm just going to shorten this so I have room here. 3.03 times 10 to the negative 11 over 1. Just closing my bracket there. So if we plug this into our calculator, we get E equals 6.626 times 10 to the negative 34 times 3 times 10 to the 8 multiplied by 3.572 times 10 to the 8. And plugging all of this into the calculator, we get that the energy gained by the electron due to the elastic collision is 7.1012 times 10 to the negative 17 joules. To finish off, I would just like to say I like physics and I'm good at solving problems. Thanks, Charles.